Thank you. So I'm going to present some progresses and challenges on modern studies, and also briefly introduce recently proposed and planned model comparison activities. As we know, during recent years, there are a large number of modern studies looking at linkage between Arctic climate change and mid-latitude climate and weather. So some modern studies find statistically significant signal supporting this linkage, but there are still other modern studies showing the different results, arguing about this linkage. So I'm going to show a couple of recent modeling results in the next two slides. This is one study conducted by South Korea group. So they look at the Arctic forcing, regional forcing on the regional response in the mid-latitude. They use the GFDR fully coupled model, but they not model the SST to observe the SST north of 70 degrees north from 1950 to 2013. And then they analyze the model output by regression analysis. So they found that there is a statistically significant correlation between Barents Sea, Kara Sea temperature and the Eurasia landmass temperature. And also there is the high correlation of the surface air temperature between Chukchi Sea and North America. So that means there is a strong correlation relationship between Arctic warming and the mid-latitude cooling in both regions. And then they apply the same regression analysis to the CMAP5 modeling results. So they found this is the regression coefficient. So the multi-model mean regression coefficient capture the negative correlation between the Arctic warming and the Eurasia cooling, and also North American warming and Arctic warming and the North American cooling. So this is a modeling results by Korean colleagues. But however, when we look at the other modeling studies, the Environment Canada group used their own fully coupled model. They contacted 50 ensemble model simulations, and then they look at the CS concentration in the Barents Sea and the Kara Sea, between the changes between recent 10 years and in 1980s. This is the histogram. We can see the almost all model simulations capture the decrease of the CS concentration in the Barents Sea and the Kara Sea area. The ensemble mean CS decrease will capture the observed CS decrease in this area. However, we look at the Eurasia surface air temperature changes. They found the surface air temperature only show the increase in signal. But this is completely different from what we have observed in recent decades over the Eurasia. But they try to detect if the Barents Sea CS decrease really causes cooling over the Eurasia. They did the correlation analysis and then isolate a component of surface air temperature change associated with the CS decrease in the Barents Sea and the Kara Sea. They really found that there's a decrease of surface air temperature, but the magnitude is much smaller than the observed one. And then from this modeling study, they conclude the decrease, recently observed the decrease of surface air temperature could not be attributed to the CS decrease in the Barents Sea and the Kara Sea. So from these two studies, we can see there are still uncertainties. In the modeling study, we're looking at the Arctic and the mid-latitude linkage. So in the modeling studies, in addition to simulating the observed changes between Arctic and mid-latitude, So all the modern studies have also tried to understand the physical processes behind those observed or simulated relationship between Arctic and mid-latitude. So this slide shows the pathways, atmospheric dynamics pathways, how Arctic forcing through these pathways influence the mid-latitude climate and weather. So Judy already introduced the study by Kim et al. The Arctic forcing influence the atmosphere circulation through interactions with the stratosphere. This is the other study from our collaborative team. So the Arctic forcing can trigger upward raspberry wave propagation. So the convergence of EP flux decelerate the vessel's or jet stream. So both, okay, the forcing signal through both ways will finally cause phase transition of Arctic oscillation. So when Arctic oscillation changes from a positive phase to the negative phase, there will be cold events occur over Eurasia. So from these studies, we can see the phase transition of Arctic oscillation or North Atlantic oscillation will be key to link Arctic forcing and the mid-latitude weather and climate. So how about model simulations about this physical process or atmosphere dynamic process? Is there any phase transition in the Arctic oscillation or North Atlantic North Atlantic oscillation in the simulated model studies? The Doug Smith provided a summary at the US Cloud workshop early this year. So they found there's a large number of modeling studies. They shows a negative phase of NAO in response to the Arctic forcing. But the other studies shows a positive NAO in response to the Arctic forcing. So we can see the different models shows a different response for this fundamental dynamic atmosphere dynamic process. So there is a large uncertainty about the simulation about this the atmosphere dynamic process. So there's the other question raises, if this Arctic oscillation or North Atlantic oscillation really play a key role in linking Arctic climate change and the mid-latitude weather and the climate. So we look at the time variations of Arctic oscillation and its driven temperature, surface air temperature changes. Because the Arctic acceleration of Arctic climate change, climate warming, and the retreat of Arctic sea ice mainly occur after mid-1990s. So we split the time period to the early time period before 1996 and after 1996. So in the early time period, we can see the Arctic oscillation is mainly in the positive phase. There's an upward trend. So the positive phase of the Arctic oscillation mainly causes the increase of temperature, surface air temperature over the Eurasia, but a decrease of surface air temperature over the North Atlantic Greenland area. This pattern is highly consistent with the observed linear trend of surface air temperature. So during that time period, we use Arctic oscillation-driven temperature changes to explain the warming trend of the Arctic. However, after 1996, the Arctic oscillation mainly went to the negative phase. So corresponding to this negative phase, there was a decrease, dramatic decrease of surface air temperature, but there's an increase of temperature over the Greenland area. It's quite different from what have been observed for surface air temperature increase in trend. So amplified Arctic warming over the center of the Arctic Ocean is missing. So in this case, the Arctic oscillation may not be really explain the systematic shift or systematic changes of surface air temperature from mid-latitude to the center of the Arctic Ocean. So what else we can think about atmosphere dynamics? So we recall what we have done some years earlier about the acceleration of Arctic warming and dramatic decrease of the sea ice. So that paper published in 2008. So during those time periods from mid-1990s to the early 2000s, so there was dramatic changes of atmosphere circulation spatial structure from this triple Arctic oscillation structure to this dipolar structures. So when we look at this dipolar structure, the center of action shift to the Eurasia continent. There's the other center of action of North Atlantic. So we give the name of this pattern as the Arctic rapid change pattern because at the same time, there was a dramatic acceleration of Arctic sea ice decrease and acceleration of Arctic warming or amplified Arctic warming. Okay. Corresponding to this negative phase of this ARP pattern, we found that there is a dramatically enhance the transport of warm and moist air into the center of Arctic Ocean, and the cold Arctic air recirculate to the mid-latitude. So we extend this analysis of ARP to the most recent years. So we found this time series of the ARP. We found after mid-1990s, there's an increase of a frequency of occurrence of extremely negative ARP phase. So corresponding to this negative ARP phase, there's amplified warming over the central Arctic Ocean, but the cold temperature occur over the Eurasia. So from the slides, what I have shown, the simulation of the surface air temperature changes has among different modern studies has a larger uncertainty. So the atmosphere dynamics simulation of atmosphere circulation dynamics also show the large uncertainty. So our US Clover working group proposed a coordinated modeling simulation. So we aim to detect solid signal from noise, from a larger internal natural variability. We also want to identify robust the physical processes behind those observed potential linkage. So the European groups got funded the project by H2020 program. So under support of this H2020 applicate project, there was the modeling group formed. So this modeling group, including US team members, so we propose a modeling comparison project. There are a number of modeling simulations proposed. So I only list two groups of model simulations here because these two groups of model simulation have been well discussed and planned. The first group is AMAP type simulations. So for the control run, the model will be forced by climatological SST and the sea ice. There are also 3 sets of sensitivity experiments. So in those sensitivity experiments, the model will be forced by pre-industry SST or future SST or pre-industry Arctic sea ice or future sea ice or Antarctic, pre-industry Antarctic sea ice or future sea ice. So there is also the second group of modeling experiments. It's mainly conducted by fully coupled model. So the for the control simulation, the simulated modeled SST will be constrained by present-day climatology, or the sea ice will be constrained by present-day climatological sea ice. So there's also 2 sets of sensitivity experiments. So for one set of experiments, the CIS will be constrained by pre-industry CIS or future CIS. In the other set of modern experiments, the Antarctic CIS will be constrained by pre-industry CIS or future CIS. Here is my summary. So there is no consensus reached among the modern studies so far. So the dynamic processes linking Arctic and the mid-latitude has not been well understood. So this also impacts the selection of metrics to evaluate model performance. So there are also a number of other uncertainties and challenges listed here, but because of limited time, I have not been include slides talking about that. So we also propose the modeling efforts to coordinate modeling experiments and analysis. The PA and PA MAP project will be the greater contributing component to these coordinated modeling efforts. So I'm ending here. Okay, thank you.